Good evening, everyone. Thank you for joining us early. Our math tutorial live stream will begin in 5 minutes. Please stay tuned as we prepare to go live. Good day, everyone. Welcome to our math tutorial live stream. I'm Chloe, and I'll be guiding you through today's lesson together with my group mates. Today, we'll be discussing triangles and circles, and we'll show how these concepts can be applied to real-life situations, such as planning flood warning speaker coverage for our barangays in our math IPBA. Again, good evening, everyone. Welcome to our math tutorial live stream on understanding triangles and circles. We are the group 2 of the grade 10-3 online class, and today we aim to make geometry easy, visual, and fun. Whether you're reviewing for a test or open assessment, or you simply want to better understand triangles and circles, this session is designed to help you learn step by step. Throughout this live stream, we'll use clear visuals and guided examples to help you follow along. Let's get started with our first topic, triangles. What are our learning goals today? By the end of this tutorial, you should be able to identify different types of triangles, understand how right triangles work, and use special right triangles and trigonometric ratios to find missing sides. Most importantly, you'll be able to apply these ideas to real-life situations, such as finding heights and distances using angles of elevation and depression. What is a triangle? And why are they important? Because triangles are the strongest, most stable geometric shape used in engineering, architecture, bridges, and structures. A triangle is a polygon with 3 sides and 3 angles and 3 vertices. Triangles are one of most important shapes in mathematics because many real-life situations, such as measuring distances, heights, and directions, can be modeled using triangles. A triangle is a three-sided polygon whose interior angle sum is always 180 degrees. This concept can be used to find the measurement of an angle, given the measurement of two angles. In the given example, if angle A equals to 50 degrees and angle B is 60 degrees, find angle C. Solution. Angle C equals to 180 degrees minus the sum of angle A and angle B. Then, substitute. Angle A equals to 50 degrees. Then angle B to 60 degrees. Then simplify to get angle C equals to 70 degrees. Before we go further, let's review the basic vocabulary. A triangle is a polygon with 3 sides and 3 angles. A vertex is a point where two sides meet. Side is a boundary line of the triangle. Angle is a space by two intersecting sides. Interior angle is a angle inside a triangle. Exterior angle is a angle outside, formed by extending a side. Altitude is a perpendicular line from vertex to the opposite side. Median connects a vertex to the midpoint of the opposite side. Angle bisector divides an angle into two equal parts. Types of angles in triangles. Triangles can be classified by their angles. An acute triangle has all angles less than 90 degrees. A right triangle has exactly one 90-degree angle. An obtuse triangle has one angle greater than 90 degrees. Today, we will focus mostly on right triangles because they are used in trigonometry. Types of triangles by sides. Triangle can also be classified by their sides. An equilateral triangle has all sides equal. An isosceles triangle has two equal sides. A scalene triangle has all sides of different lengths. Special right triangles come from isosceles and equilateral triangles. Parts and properties of a right triangle. In a right triangle, the side opposite the right triangle is called the hypotenuse, the longest side. The other two sides are the legs. Depending on the angle we are working with, one leg is called the opposite side, and the other is the adjacent side. Say, in the given triangle, angle A, the opposite side is the side across the angle, and the adjacent side is the side next or besides the angle. Right triangle follow important properties. In a right triangle, one angle is 90 degrees, so the other two angles must be acute and complementary. The Pythagorean theorem applies only to right triangles. Let's do a quick recap. A triangle is a figure with three sides, three angles, and three vertices. Understanding triangle is important because many real-life problems can be modeled using them. The basic parts of a triangle are the sides, angles, and vertices. Knowing these parts help us identify what is given and what we need to find. In a right triangle, one angle is 90 degrees. The side opposite the right angle is the hypotenuse. and it is the longest side. The other two sides are the legs, which we call the opposite and adjacent sides depending on the angle. Understanding these parts and properties is important because all the formulas we use later are based on them. With that foundation, we are now ready to study the relationship between the sides of a right triangle. Now that we understand the parts and properties of a right triangle, we're ready to learn how the side lengths are related. This relationship is described by one of the most important formulas in mathematics, the Pythagorean theorem. To discuss this next topic, I will now turn the discussion over to Jiraiya.
Good day everyone, I am Jiraiya. Today I will explain the Pythagorean theorem. So, the formula is a squared plus b squared is equals to c squared. Here, a and b are the legs of the right triangle, and c is the hypotenuse, which is the longest side. Okay? So this formula is only used for right triangles, meaning triangles with 90 degree. So let's move to the next example. Okay? We are given a equals to 5, b equals to 12, and we are finding c. Since we're solving for c, we rewrite the formula as c is equals to a squared plus b squared. Now, we substitute the values. C squared equals 5 squared, since a is equals to 5, b is equals to 12. So it becomes like that. So 5 squared is 25 and 12 squared is 144. So after substituting, we simplify. C squared equals 25 plus c squared equals 169. Now, to solve for c, we take the square root of both sides to remove the exponent. C is equals the square root of 169. And since the square root is 100, the square root of 169 is 13, so c is equals to 13. Okay? Okay, let's move on to the next example. Next, we are given a is equals to 9, c is equals to 15, and now we're trying to find b. We start with a squared plus b squared equals c squared. Since b is not alone, we need to rearrange the equation. We move 8 to the other side. When a term moves to the other side, its sign changes. So we get b squared equals c squared minus a squared. Okay, now we substitute the values. So c is equals to 15 and a is equals to 9. So it becomes b squared equals 15 squared minus 9 squared. Okay, so 15 squared is 225 and 9 squared is 81. After substituting, we can simplify. B squared equals 225 minus 81. We show the equation first. B squared equals 144 since we simplified it. Okay? To solve for b, we take the square root. Okay? So B is equals to 12. Okay? And the last example, we are given B is equals to 7 and C is equals to 25. And we are trying to find A. Okay? So, we start with A squared plus B squared equals C squared. So, isolate A squared, we move B squared to the other side. So, the equation becomes A squared equals C squared minus B squared. Okay? So, now, we substitute the values. Okay? So, C is equals to 25 and B is equals to 7. Substitute. So, it becomes A squared equals 25 squared minus 7 squared. Important reminder here. We use 7 squared, meaning 7 times 7. We do not use a negative 7. Even if we're negative 7 times negative 7, it will still become positive 49. So, A squared is equals to 625 minus 49. 7 squared is 49. 25 squared is 625. Okay, after substituting, we can simplify. There. A squared equals 625 minus 49 is equals to 576. Now, to solve for A, we take the square root of both sides. The square root of 576 is 24. So A is equals to 24. So remember, we rearrange the formula to isolate the missing side. Okay? Substitute the values. We simplify first, show the equation with the square, then take out the square root. That's all, and thank you. Bye!
Let's do a recap of what Uriah discussed. The Pythagorean theorem applies only to right triangles. It describes the relationship between the lengths of the sides of a right triangle. If A and B are the lengths of the legs, and C is the length of the hypotenuse, then the relationship is A squared plus B squared equals C squared. This formula allows us to find a missing side length of a right triangle when the other two sides are known. Why the Pythagorean theorem is important. The Pythagorean theorem is important because it helps us measure distances that are not easy to measure directly. Now that we understand the relationship between the sides of a right triangle, we can move even faster in solving problems. Some right triangles follow special patterns where the side ratios are always the same. Knowing these patterns allow us to find sine legs quickly, sometimes without even using a calculator. To discuss these special patterns in right triangles, I will now turn the discussion over to Nerine, who will introduce special right triangles.
Hello everyone. Let's talk about the special right triangle. The 45-45-90 special right triangle. This is the most useful shortcut shapes. What makes it special? Special right triangle allow us to avoid calculators. Once you memorize all these ratios, you can immediately find the exact side of the length, which is very helpful for us. Now let's check the side ratios. This 45-45-90 special right triangle has two equal angles, so the side opposite them are also equal. If each leg has a length of 1, the hypotenuse is square root 2. Here we have the angles. We have two 45-degree angles and one 90-degree right angle. Since the two angles are equal, meaning its two legs, the sides forming the right angle are always the same length. This formula allows us to move from one side of a 45-45-90 triangle to another easily. Just remember, the hypotenuse is always square root 2 times longer than each leg. Here you go, the example. Last time, we covered how to find the hypotenuse when we know the legs of a 45-45-90 degree triangles. What if we know the hypotenuse and needed to find the length of the equal legs? Legs are equals, and the hypotenuse equals leg multiplied square root 2 to find the leg when we have the hypotenuse. We just rearrange that formula. Remember the core ratio. A square always creates a 45-45-90 triangle when we draw a diagonal. Since both legs are equal, we simply multiply by the square root 2 the leg to solve the hypotenuse. Now, we understand the concept of the 45-45-90 triangle. Let's apply it to a real problem. As you can see, guys, we have two problems here. Let's check the first one. Here you go. The first problem, we know one leg is 9 cm and we need the hypotenuse. We need to find the hypotenuse. Remember our core formula. For a 45-45-90 triangle, hypotenuse equals leg multiplied square root 2. Here the leg is 9 cm. So let's plug that in. Hypotenuse equals 9 multiplied square root 2 is equals 9 square root 2 cm. And that's it. Since 9 square root 2 can be simplified further, that's our answer. Next problem. The second problem, we have the hypotenuse already, which is 20 cm here. And we need to find the length of each equal leg. We rearrange the formula for this case. Leg equals hypotenuse divided by square root 2. Or to make it easier to calculate, we rationalize the denominator. Leg equals hypotenuse multiplied square root 2 divided by 2. Again, we rationalize the denominator. Leg equals hypotenuse multiply square root 2 divided by 2. Let's use the rationalized version here. Leg equals 20 divided by, leg equals 20 multiplied square root 2 divided by 2 equals 10 square root 2 cm. Here you go. Next slide. Let's take what we know about 45-45 triangles and use it to solve a real-world problem. Let's check this out. So we have a square part and each side has 20 meters long. When we draw a diagonal from one corner to the other, that diagonal splits the square into two identical triangles. What kind of triangles? Let's see. A square has all right angles and equal sides, so the triangle formed has a 90-degree angle and two 45-degree angles. It's a 45, 45, 90 special right triangles. The sides of the square are the legs of the triangle. So each leg is 20 meters long. Remember the formula for the 45, 45, 90 triangles. The hypotenuse equals leg multiplied square root. The diagonal of the square is the hypotenuse of the triangle. Plugging in our leg length, diagonal equals 20, multiply square root 2 equals 20 square root 2 meters. That's the exact length of the pathway. We've mastered the 45, 45, 90 triangles. Now let's meet another special right triangle. This is the 30, 60, 90 triangle. This triangle is very common in word problems. Always start by identifying the side opposite. The 30-degree angle, that's the shortest side. Unlike the 45, 45, 45, 45, 90 triangle, all sides here are different lengths. As you can see, we have 30, 60, and 90. So, but still, the ratio stays the same every single time. Remember, shortest leg opposite 30 degree, longest leg opposite 60 degree, and our hypotenuse is twice the shortest leg. First, let's talk about the patterns. Every 30, 60, 90 triangle follows the same rule. The shortest side, it's always across from the 30-degree angle. We just call it x. That's our starting number. The longer side across from 60 degree is just x times square root 3. We just write it as x square root 3. The longest side, our hypotenuse across from 90 degree, is double the shortest side. So, it's 2x, as you can see here. Let's try with a real number to see how it works. Say the shortest side is 5. So, x equals 5 here. And our longest side, just 5 times square root 3. So we have 5 square root 3. And for our hypotenuse, just double the 5 and it will be 10. See? It's just plugging in the number for the x. Remember, start with the shortest side and then multiply by square root 3 for the longer one. And double it for the hypotenuse. And that's all. Next slide. Alright, what if we don't know the shortest side, but we do know the longest one, the hypotenuse. Remember, the hypotenuse is double the shortest side. Well, to go backwards, just split the hypotenuse in half to get the shortest side. If the hypotenuse is called x, the shortest side is x divided by 2. Here you go. Then the longer side, take that shortest side and multiply by square root 3. So it will be x square root 3 divided by 2. Let's try with a number. Say hypotenuse is 16 and the shortest side will be 8 because we split the 16 in half. So it will be 8. Here you go. And the longer side, take that 8 and multiply by square root 3. So it will be 8 square root 3. Okay, as you can see for this picture, the ladder is leaning against the wall, so it makes a triangle shape. The ladder itself is the longest side, which is hypotenuse of a 30, 60, 90 triangle. We know two things. The ladder is 10 meters long and it makes a 30-degree angle with the ground. Here, as you can see, remember our rule, the hypotenuse is double the shortest side. So if the hypotenuse, which is the ladder, is 10 meters, we just need to split that in half. So if we will split that in half to get the height on the wall, 10 divided by 2 is 5. So the ladder reaches 5 meters high on the wall, and 10 divided by 10 divided by 2 is 5, so the ladder reaches 5 meters high on the wall. That's all. We just match the real thing to our triangle rules. Next, let's figure out flagpole problem. It's just like the ladder one, but with a cool twist. Okay, in this picture, the flagpole stands straight up. The rope goes from the top of the pole to the ground, as you can see here, and the ground is flat. So we've got 30, 60, 60, 90 triangle again. The rope is the longest side, the hypotenuse. This is our hypotenuse. It's 12 meters long. The rope makes a 60-degree angle with the ground. So the angle between the flagpole and the ground is 90 degree, which means the last angle must be 30 degree. Remember our golden rule? The shortest side is half the hypotenuse. So if the rope is 12 meters, we just cut that in half to get the distance we need. 12 divided by 2 is 6. So the anchor of point is 6 meters away from the base of the flagpole. So even though the angle here is 60 degree, we just find the 30-degree angle and use our half the hypotenuse tree. And that's all. I hope you had fun while learning our topic, which is the special right triangles. Thank you so much.
Let's quickly recap what Nerine discussed. Special right triangles are right triangles with specific angle measures that always produce the same side ratios. In a 45-45-90 triangle, the legs are equal and the hypotenuse is the leg multiplied by the square root of 2. In a 30-60-90 triangle, the shortest side is the opposite the 30-degree angle, and the side lengths follow the ratio 1 to the square root 3 to 2. This pattern helps us find side lengths faster and more accurately. Now that we understand special right triangles and their side ratios, we are ready to take the next step. Special right triangles give us fixed ratios for specific angles. But what if angle is not 30 degrees, 45 degrees, or 60 degrees? This is where trigonometric functions come in. Trigonometric functions describe the relationship between the angles and the side lengths of any right triangle. Instead of memorizing side ratios, we use sine, cosine, and tangent to find unknown sides or angles. Let's now explore these trigonometric functions and how they help us solve real-life problems.
Hi everyone, today I'm gonna discuss about trigonometric function. Now that we understand the parts of a triangle and the concept of right triangles, we move to something very powerful. The angle of elevation is the angle formed when an observer looks upward at an object. Trigonometry helps us find something sides and angle in right triangles using simpler ratios, sine, cosine, and tangent. Instead of measuring directly, we can calculate accurately. In an angle of elevation problem, opposite side height of the object, adjacent side horizontal distance. The, this is important because many real life situations form right triangles, like measuring the heights of building, the distance across a river, the, the slope of a road, or the angle of elevation and depression. This formula is used to find heights that cannot be measured directly. When we understand trigonometric function, we can determine and know measurements, analysis, relationship between angles and sides, and solve practical problems using logical steps and formulas. The angle of depression is the angle formed when a observer looks downward and at object. The angle of elevation and the angle of depression are equal in measure. They are alternate ulterior angles formed by parallel horizontal lines. In short, trigonometric terms triangles into tudes for measurement and problem solving in the real world.
Before we proceed, let's recap the concepts discussed by Katrina: the angle of elevation and the angle of depression. The angle of elevation is formed when we look upward from a horizontal line to an object above us, while the angle of depression is formed when we look downward from a horizontal line to an object below us. A key idea to remember is that these two angles are equal when they share the same line of sight and parallel horizontal lines, which allow us to model real-life situations using triangles. However, when the triangle formed is not a right triangle, especially in distance problem, like locating a speaker station relative to a barangay center, we need a different approach. This brings us to the law of cosines, which we will now use to compute distances more accurately. We will be discussing trigonometric ratios, especially sine, cosine, and tangent. Let's begin. Trigonometric ratios help us understand the relationship between the sides and angles of a right triangle. This topic is very important because it will help us solve real-life problems involving heights, distances, and angles. These are ratios that compare the side of a right triangle based on a given angle. We only use these ratios for right triangles, and we always focus on one acute angle at a time. Before using trigonometric ratios, we must identify the parts of the triangle. The hypotenuse is the longest side and is always opposite the right angle. The opposite side and the adjacent side depend on the angle we are focusing on. In the given illustration, this is the angle we are focusing on. The opposite side is the side across the angle, which is this side, and the adjacent side is this side next or beside the angle this side. But what if the angle we are focusing on is the other angle, the opposite side? The side across the angle is now this side, and the adjacent side, the side next the angle, is now this side. To easily remember the trigonometric ratios, we use SO, KA, TOA. SO means sine, is opposite over hypotenuse. KA means cosine, is adjacent over hypotenuse. TOA means tangent, is opposite over adjacent. Sine of an angle is the ratio of the opposite side to the hypotenuse. Whenever the problem involves these two sides, the sine is the correct trigonometric ratio to use. Cosine of an angle is the ratio of the adjacent side to the hypotenuse. This is used when the side next to the angle and the longest side are given. Tangent of an angle is the ratio of the opposite side to the adjacent side. Notice that tangent does not involve the hypotenuse. Let's try an example. Given a right triangle with angle theta, if the opposite side is equals to 3, adjacent side is equal to 4, and hypotenuse side is equal to 5. Find sine theta, cosine theta, and tangent theta using SOHCAHTOA. SO means sine, is equal to opposite over hypotenuse. Substitute. Opposite is equal to 3. Hypotenuse is equals to 5. Thus, sine theta equals 3/5. Ka means cosine, is equal to adjacent over hypotenuse. Substitute, adjacent is equals to 4 and hypotenuse is equals to 5. Thus, cosine theta is equal to 4/5. TOA means tangent, is equals to opposite over adjacent. Substitute, opposite is equals to 3 and adjacent is equals to 4. Thus, tangent theta is equals to 3/4. Finding an angle using inverse trigonometric function. In this example, the trigonometric ratio is already given. Sine theta is equal to 3/5, and we are asked to find the angle theta. Since sine of the theta is 3/5, we are going to apply the inverse sine function. Using the calculator in scientific, degree mode, and inverse trigonometric function by clicking the second. Then we type 3 divided by 5, then inverse sine, and that will give us an angle of approximately 36.87 degrees. Finding a missing side using trigonometric ratios. Given an angle and a side, find a missing side. In this problem, an angle 45 degrees and one side. The hypotenuse, which is equals to 12, are given, and we are asked to find another side, the opposite side. Since the opposite side and the hypotenuse are involved, we will use sine. Sine theta equals opposite over hypotenuse. Substitute sine theta is sine 42 degrees, and hypotenuse is 12. Multiply by both sides of the equation by 12. So remove the fraction. That will give us 12 times sine 42 degrees equals the opposite side. Then we get the value of sine 42 degrees because 42 degrees is not a special angle. We use the calculator in scientific mode and degree mode. Okay, now we get the value of the sine 42 degrees by typing 42 and click sine, and that will give us approximately 0.6691. Multiplying by 12 by the value of 42 degrees, which is approximately 0.6691, it's equals to give us approximately 8.03 units. Let's pause for a short recap of what we just discussed. Trigonometric ratios describe the relationship between the angles and the sides lengths of a right triangle. In a right triangle, we focus on three main trigonometric ratios. Sine, which is the ratio of the opposite side to the hypotenuse. Cosine, which is the ratio of the adjacent side to the hypotenuse. Tangent, which is the ratio of the opposite side to the adjacent side. These relationships are commonly remembered by using so, ka, towa. Why trigonometric ratios are important? Trigonometric ratios allow us to find missing side lengths or angles even when direct measurement is not possible. Now that we understand how trigonometric ratios work in right triangles, we are ready to apply them to real-world situations. Two very important applications of trigonometric ratios are angle of elevation and angle of depression. To explain how trigonometric ratios are used in these real-life situations, I will now turn the discussion over to Katrina, who will discuss the angle of elevation and the angle of depression. What is the law of cosines? The law of cosines is a formula that works for any triangle. It is especially useful when the triangle is not a right triangle, or rather an oblique triangle, and when two sides and the included angle are known. The law of cosine is a formula that works for any triangle. It is especially useful when the triangle is not a right triangle, or rather an oblique triangle, and when two sides and the included angle are known. The law of cosine formula states that c squared is equals to a squared plus b squared minus 2ab cosine angle C, where A equals side opposite angle A, B, and C, the other two sides, A, the included angle of side B and side C. The key point is that angle A must be the angle between sides B and C. Okay, how are we going to apply the law of cosine in our math IPBA? Let's have an example. We treat the Marikina City origin as a reference point. Side A, the distance from the city origin to barangay center. Side B, the distance from the city origin to the speaker station. Angle C, the angle between the two sides. Side C, the distance between barangay center and the speaker station center. The distance from the origin to barangay center and to the speaker station form two sides of a triangle, and the angle between them is known or can be determined. The distance we want to compute is the third side, the distance between barangay center and the speaker station center, which we can find using the law of cosine. In the previous problem we had in the previous slide, we have the given data. Side A equals 1,200 meters, side B equals 900 meters, and side C is 60 degrees. What are we going to find is side C, the distance between the barangay center and the speaker station, using the cosine formula. A is equals to 1,200, B is equal to 900, cosine C is equals to 60 degrees. Cosine 60 degrees equals 0.5. Simplify. 1,200 squared is 1,440,000 plus 900 squared is 800,000, 10,000, negative 2 times 1,200 times 900 times 0.5 is equals to 1,080,000. Simplify again. C squared is equals to 1,100,000 70,000. Get the square root of both sides of the equation to derive the value of C. Thus, C is approximately equal to 1,081.7 meters. The distance between the barangay center and the speaker station center. Why is the law of cosines included in the topics to be discussed? In our Math IPPA, we need to compute the distance between the center of the barangay and the center of the speaker station. However, the triangle formed is not a right triangle, as we cannot use the Pythagorean theorem or basic trigonometric ratios. Since we are given two sides and the angle between them, we use the law of cosines. Before we move on to circles, let's briefly recap the law of cosines, which we just discussed. The law of cosines is used to find a side or an angle in a triangle that is not a right triangle, meaning there is no 90 degrees angle. We apply this formula when we are given two sides and the included angle, or when the triangle does not satisfy the conditions for basic trigonometric ratios. In our Math IPPA, we will use the law of cosines to compute the distance between the center of a barangay and the center of a speaker station, allowing us to accurately measure distances even when the triangle formed is oblique. Now that we know how to compute distances between 2 points using triangles, we are ready to move on to circles. Circles will help us model coverage areas, such as how far a speaker station can reach, using concepts like radius, center, and distance. So with that, let's now proceed to our discussion on circles. Earlier, we used triangles and trigonometry to measure heights and distances that are hard to measure directly. Now, we move from measuring distances to mapping distances. Circles allow us to represent all points that are a fixed distance from a location, just like how we use distance in triangles. So instead of finding one distance using tangent, we now represent all possible distances at once using a circle equation. That is why triangles and circles work together in real-life applications, like our speaker coverage project. So what are our learning goals today? By the end of this tutorial, you will be able to describe a circle as a set of points equidistant from a center on the coordinate plane. Understand how the distance formula leads to the standard equation of a circle. Write the equation of a circle given its center and radius. Identify the center and radius from a given circle equation. Graph a circle accurately using its equation. Connect circle equation to real-life coverage problems, such as signal range and warning zones. Use Desmos to visualize and verify circle coverage mathematically. Before we use Desmos to model speaker coverage, we must understand what a circle means in coordinate geometry. A circle is not just a drawing. It is a set of points that are all the same distance from a center. Circle on the coordinate plane. A circle is the set of all points in a plane that are the same distance from a fixed point called the center, and the distance from the center to the circle is called the radius. When a circle is drawn on a coordinate plane, we can describe it using an equation. The distance formula is the foundation of the circle equation. Using the distance formula to get the distance between 2 points. D equals square root of quantity x minus h squared plus y minus k squared. If the distance from point xy to the center hk is always r, the radius, then square root quantity x minus h squared plus quantity y minus k squared equals r. This formula is the reason why the circle equation works. Every point on the circle is exactly r units away from the center. That idea comes directly from the distance formula. Now, let's discuss the standard equation of a circle. By squaring both sides of the distance formula that we have in the previous slide. Square root of quantity x minus h squared plus quantity y minus k squared equals r. We derive the standard equation of the circle. Quantity x minus h squared plus quantity y minus k squared equals r squared, where hk is the center and r is the radius. This is the exact equation we type into Desmos to visualize coverage. Understanding each part of the formula. Students often memorize this formula. Instead, understand it. These parts measure how far a point is from the center, horizontally and vertically. XY is any point on the circle. HK is the fixed point, the center of the circle. R, the radius, the distance from the center of the circle to the point XY. Writing the circle equation. Okay, let's learn how to write the circle equation giving the center of the circle and its radius. We have the center, HK, equals 3, negative 2. And the radius, R equals 4. Using the standard equation of the circle, quantity x minus h squared plus quantity y minus k squared equals r squared. Substituting, we get the equation quantity x minus 3 squared plus quantity y plus 2 squared equals 4 squared. Writing the equation is simple. Substitution. Just replace h, k, and r. Notice the sign changes for negative coordinates from -2 to +2. We will discuss the step-by-step in the next slide. Let's learn the step-by-step how to write a circle equation. Using the previous example we have in the previous slide. Step 1. Identify the center, HK. 3, -2. Step 2. Identify the radius, R. 4. Step 3. Substitute into the standard equation of the circle. Quantity x minus h squared plus quantity y minus k squared equals r squared. H is 3. K is -2 to +2 since 2 is negative. R is to 4. Step 4. Simplify file. The image appears on the graph with 4 corner points. If no corner points appears, you may click here or the picture itself. You may drag those points to resize the image by dragging one of the corner points. Or change the value of the width. And height. Then zoom out at the top right. You may change its position to align with the coordinates by navigating in the middle point. A compass-like symbol appears. Then hold and drag it to your desired position. Okay, we'll save this for now and we'll be using this later when we have the barangay's coordinates. Why this matters for our project? Now you can see why learning the circle equation is important. The speaker station coverage and the barangay zones are both circles, which we model using the standard equation of circle. Quantity x minus h squared plus quantity y minus k squared equals r squared. Desmos can graph these equations to verify full coverage. It will show whether our plan truly covers the area. With this background, we're ready to open Desmos and type the equations that represent real-life coverage for Malanday, tumana, and nangka. Now, we know how to write circle equations for each barangay. Write circle equations for each speaker station. And use Desmos to confirm coverage visually. Flood warning speaker coverage proposal. Today, we will present our mathematical proposal for placing high-powered speaker station to ensure flood warnings can reach residents in 3 barangays: Malanday, Tumana, and Nangka. Using concepts from triangles, trigonometry, circles, and coordinates geometry we just learned, we designed a system that the local government can visualize using a navigation tool like Desmos. We are given that each speaker station can cover a radius of 500 meters. Each barangay also has required warning zone. Malanday must be warned within 872.5 meters of its center. Tumana within 877.5 meters. Nangka within 1,086.7 meters. Our goal is to make sure that every point inside those zones is within 500 meters of at least one speaker station. To model this mathematically, we use a coordinate plane. Marikina City is the origin at 0, 0. West is negative x, east is positive x, and north is positive y. Using the given distances, we convert the barangay locations into coordinates. Malanday, the center is 1,239.5 meters. West, negative x. So, negative 1,239.5 and 131.9 meters. North, positive y. So, 131.9. Tumana, the center is 812.3 meters. West, negative x. So, negative 812.3 and 1,167.3. North, positive y. So, 1,167.3. Nangka, the center is 447.5 meters. East, positive x. So, 447.5 and 2,152 meters. North, positive y. So, 2,152. What strategy are we going to use for the speaker station? First, we will cover the center of the barangay, meaning the center coordinate of the speaker is the same with the center of the barangay. But with a radius of 500 since the speaker station can only cover within 500 meters radius. Then, we'll be placing additional speaker stations around the center speaker stations. Cover the boundary and minimize the gaps. For the barangay zone or coverage, the circle equation is quantity x minus h squared plus quantity y minus k squared less than or equal to r squared. As what we have learned in the previous slide, we need the center coordinate and the length of the radius to derive the circle equation by simple substitution. For example, Barangay Malanday. The center is negative 1,239.5, 131.9, and radius is 872.5. We just simply substitute in the standard equation of the circle. H equals negative 1,239.5. Since it is negative, it becomes positive. K equals 131.9 and R, the radius, 872.5. For Tumana and Angka, we follow the same substitution. For speaker station coverage, we are going to use the equation quantity x minus h squared plus quantity y minus b squared less than or equal to 500 squared. Now, we are going to graph circle equation in decimals. First, we are going to graph Barangay Malanday. First, open decimals. Next, copy Malanday sender coordinate, then label it Malanday. Then copy Malanday's circle equation. As simple as that. You can do the same with the other two barangays, Tumana and Nangka. What did we learn today? Today, we didn't just study triangles and circles separately. Triangles and trigonometry helps us measure distances we cannot measure directly. Circle equation help us represent all possible points that are the same distance away. And Desmos allowed us to see this mathematically and visually. That's how mathematics helps solve real community problems like planning flood warnings for our barangays. Now that we're ready, let's move on to our Math IPBA. In the previous slide, we uploaded the map of Marikina in Desmos, and we will now use the map we saved earlier. Looking at our given data, let's first make a rough estimate for the height. or the y-coordinate. Nangka is the barangay farthest to the north of Marikina City. Its center is about 2,252 meters north of Marikina City, which is our point of origin. To simplify, we'll round this to 2,500 meters, plus from its center to the top another 2,500 meters, a total of 5,000 meters. We then double this value to the count of the opposite direction, another 5,000 meters south of the origin, giving us a total height of 10,000 meters. Now for the width, or the x-coordinate range. The barangay farthest to the west is Malanday. Its center is 1,239.5 meters west of the origin. We'll round this to 1,500 meters and double it, that will be 3,000, just like we did earlier. Adding another 3,000 meters to the east, giving us a total width of 6,000 meters. With these estimates, let's now update the height and width values in the image box. Then click zoom out on the top right. Let's plot the coordinates of Marikina City as a point of origin. And then Malanday. And then Tumana. And then Nangka. Let's now drag the map to position and align with the coordinates. Now, we will graph the three barangays using the circle equations we learned earlier to help us visualize the covered area of each barangay. We will start by graphing Barangay Malanday. Followed by Barangay Tumana. And then Barangay Nangka. Next, for our speaker stations, our strategy is based on geometry and symmetry. To avoid gaps, we place one speaker at the center of the barangay, then additional speakers around it in a circular pattern. Okay, for Barangay Malanday, our speaker station will be placed at the center of the barangay. Since the speaker station covers the center, it will the same coordinates at the center of Barangay Malanday. We would like to thank everyone for taking the time to attend our math tutorial live stream.